Hilfe. Yeah, just give me a second. Huh? No. No. Sure, why not? Hi. Probably should turn the light a bit. Hallo. Now, wait. Like this, I would guess. Think? I kind of figured it out, oder? Right? Can you hear me? I have no idea if you can hear me. You should be able to, right? Mic is muted. Most likely the chat is a bit delayed. Guessing. Awesome. My cat is screaming in the background. Nice. Since I haven't prepared anything, I don't know. Depends on you how interesting this live stream gets. I also have no idea how many of you are just YouTube viewers only, and how many of you are actually coming from Discord to use this as a substitute for the seminar, which I normally held on Sunday, but no idea what I'm going to present today. So I'm just letting you decide on what we are going to talk about. So I got 2 books. Got the Einführung in die Kernchemie, Introduction to Nuclear Chemistry or Radiochemistry, however you would like to call it. And hello. And the Grundzüge des praktischen Strahlenschutzes. So basics on practical radiation protection. Yeah. And of course, the other chemistry books, which pretty much every chemistry student is required to at least have access to, I guess. For example, the Hollemann-Wieberg, Inorganic Chemistry. This is part 2. And this one is about the transition metals, lanthanoids and actinoids, and transactinoids. And there's an even thicker one regarding the main group elements. Can you talk about thorium fuel? Could try my best. Thorium fuel. All right. Let's freestyle that one. I haven't taken the reactor lecture that we have in our university because my professor is pretty much the only professor at the university who teaches nuclear chemistry. And he was basically teaching for the last 2 years every semester, so like the 4th time in a row, the technetium lecture. And he usually alternates between the technetium one and the reactor one. But since we had this big pertechnetate project, which I made a video about, technetium chemistry, he was basically introducing everyone to technetium. So I never got to see the reactor lecture because I've only been in nuclear chemistry for the last 2 years. So the great thing about thorium fuel means that, first of all, we only have one isotope. For example, for uranium, we have 0.72% of uranium-235. Is it squeaking too loud? I don't know. And 99.928% roundabout uranium-231, and the cross section is really low, and this one is really high. The cross section for this one, sigma F for fission, is also pretty low, but you can turn via N gamma and then beta minus decay. Sounds quick. Oh, nice. You can turn the thorium 232 via neutron irradiation into thorium 233, a beta minus emitter, which decays into the protactinium 232 and then into uranium 233, sorry, and which has a really high fission cross section, meaning that you can easily skip the whole chemistry turning into uranium hexafluoride and then ultra centrifuges and then separating out the fissionable isotope from non-fissionable isotope, because all of the thorium that you have is basically able to be turned into fissionable uranium-233. 1 second, I will look up the cross sections of these ones from the chart of nuclides. I'm sorry, I'm not pulling out the NDS web. Also, I think I could, but much faster on the chart of nuclides. Of course, it's a bit less accurate, but I think that's okay. So this one has a half-life T1/2 of 22.3 minutes, which decays then into protactinium, and with a half-life of 23 days, 27 days, sorry, turns into uranium, and this one has a half-life of 150 years, 150,000 years, and has a sigma cross-section of 530 barns, where, for example, the ones that you have to put through a lot of chemistry and a lot of infrastructure has a cross-section of 586 barns. So quite similar, without the ultra centrifuges and tons of silver in those centrifuges, and you can just take thorium 132. And the great thing is, you don't have to separate out isotopes, you have to separate out elements. Most of the time, they just are in just one big batch of thorium tetrafluoride. This could be then like in situ. So you have this big batch, you irradiate that, and while using the neutron flux to make thorium 233, you could also use the same neutron flux to fission the uranium 233. But I'm not quite sure how that's done in the industry. I've seen people do chemistry with pure uranium 233 as an oxide, as a dioxide. The what's his name called? Tom Albrecht Schönsaat, Professor Schönsaat in USA. He has a picture on Twitter with pure uranium 233. So you can separate them out, which is much more easy because thorium and uranium have different chemistry. You can separate them out, but you could also just do one big batch, irradiate that with neutrons, and turn this one into new fuel and split the current fuel. And well, there's more thorium than uranium on the Earth. How can we validate that? We just look at the natural occurring decay chains. Of course, we have the uranium-radium chain, so which includes the uranium 238, which then turns into lead-206. Then we have the uranium-actinium chain involving the uranium 235, which turns into, what was that? lead-207. Might want to look that up. Or we can, it's faster to look that up on the isotope browser app. Yeah, or thallium-205. And then we have the thorium decay chain, which involves the thorium-232, which then ends in the lead-208. And as we can see, we have, from the isotopic distribution of the different lead isotopes, we have a lot of, you can't see that, a lot of lead-208 compared to the other isotopes. Give me these numbers. Yep, it's 52% of this isotope, 24% of this one, and 22% of this. So we have a lot of lead-208, which is explained by us having more thorium naturally occurring on Earth, which can decay, leading into this isotope rather than the other twos. Which is a very ad hoc explanation, but you get the point. We just have a lot of thorium. We can use the thorium-232 to turn into uranium-233. But, of course, this can also be used for weapons, right? It's a bit more active, so it's a bit harder to handle because this one is quite stable with a half-life of 700 million years, 150,000 years. So this would have a very high specific activity, meaning that handling quantities that involves, well, weapons would be a bit more difficult for this isotope than for that isotope. Yeah. Of course, you can make the argument, if you use thorium, we would have, I don't know, less of a chance of doing weapons. Yes and no. And I've heard an argument that you would have less radioactive waste. I don't know the fission yields of the uranium-233. Should be similar to this one. I don't know that. But of course, you can transmutate the fuel to shorter-lived ones. This isn't done commercially in Germany because we don't have commercial nuclear power plants anymore. Yeah, that was an argument. I'm not on the most up-to-date state when it comes to that. So this was me talking about thorium fuel because I have no idea about reactors. Anything else? Should make. Sure, why not? Think you would do that in a fast breeder reactor? I mean, they exist. There are reactors that are specially designed for making plutonium-239, which could then be used for energy. Electricity, of course. Yeah, there are power plants that run on plutonium. As I said before, I'm not the most educated person about when it comes to nuclear fuel. I'm not the basics. But on a serious note, if you are interested in nuclear chemistry or seeing the most exotic pictures of elements up to Einsteinium, I think. Has he posted Einsteinium? Not quite sure. I know he has pictures of Californium on his Twitter account. Follow Professor Schönsaat. He just casually posts, "Oh yeah, I just cooked up another Californium crystal. Have a look at that." And I was like, I want that on my channel. And he just casually posts that on Twitter. Was a time back then, a few years ago, where very many nuclear chemists were on Twitter and were just posting stuff like, "Yeah, I just made this fucking Neptunium complex. Have a look at that. It's green." Stuff like that. And it's not that anymore. But his Twitter account, even though he's not that active, Thomas Albrecht Schönsaat. Yeah. TS Actinides. He just look at the media and he has the most beautiful pictures of radioactive stuff. Like, theoretically, would radioactive decay stop at absolute zero and speed up at absolute hot? No. The decay does not care if the atom is moving or not. For alpha decay, for example, you can estimate that to be a tunneling, quantum mechanic tunneling, and this is just absolutely random. Since the atom itself is moving and not the shape of the atom is forming around. Like if you have absolute hot, they would just wiggle around like this. But the helium nucleus that is inside that wants to be emitted as an alpha particle doesn't get anything from this movement unless the core or the nucleus itself would just vibrate back and forth. With it doesn't. When it comes to heat, it just moves, but in the same shape. Since the shape doesn't alter, the alpha decay wouldn't be affected. I think it's just less common. Yes, all of the pictures are online. Just look up the Twitter account of Albrecht Thomas. Just scroll down. It's great fun. Sometimes he posts pictures of nature. Sometimes he posts pictures of fucking radium crystals. Then just go back and see more natures, and then Californium, berkelium, or berkelium, however you would like to call it. Americium chemistry treasure. Monazite instead of thoriumite. Yeah, as I said before, monazite might be more common to find. But of course, yeah, thoriumite is basically like uraninite for thorium. Can I look up how common it is? I know monazite is somewhere in France. You can find it. But to be honest, I have another theory. I was just looking up monazite on Wikipedia. Is there actually any industry that is purely specialized on the mining of thorium? Because monazite contains a lot of lanthanides, so rare earth elements. And of course, these ones bring much more money. This is why most of these negative ion thorium shit comes from China, because China has pretty much a monopoly of rare earth production, because, well, the energy cost of producing actual usable compounds of rare earth elements like the lanthanides is quite high. But since China has very cheap labor, if you want to say it like that, and has also very cheap energy, because who cares about the environment, they are pretty much the only country where it's economically feasible to produce lanthanides. And if you just mining up monazite, which contains all of the lanthanides, and you want to generate all of the lanthanides, you will have a very large amount of thorium as a byproduct, which who knows what you're going to do with that. Yeah. So I would suggest that most people are actually mining monazite not because of the thorium, but because of the lanthanides or the rare earth elements. and just the huge amount of thorium is just a byproduct of the lanthanide production, which leads to why most of the thorium is originated from the monazite. It's just a byproduct and not the element that is especially mindful. But that's just something I've heard and something that seems logical. I don't know if that's true. I'm not in the mining industry. Hello. No, I haven't worked with neutron generators in general, with no kind of anything. We have our neutron source, our beryllium americium source. For videos, I've used the Triga research reactor in Mainz. That's it. Yeah, beryllium americium or the reactor. Nothing else. I would love to show or to make a video about neutron generators, but I'm not sure if we have one. Like near me that I could visit. I know I have a video about the cyclotron on the German channel, which is going to be released on the English channel. I just need time to translate it. I have the videos for this, like for this Tuesday and the upcoming Tuesday. I have finished, but yes, after that, I was maybe planning on doing 2 more, which are quite easy to translate, and I'm avoiding as best as I can to translate the very difficult ones, like the productinium generator experiment, or for example, the cyclotron. But eventually, I will have them translated. Yeah, maybe I'll do that next week. I'm not gonna promise anything. It looks like it's a sigma and an F. Sigma F is the fission cross section in R. Yeah, I think I can leave that there. In your home or any nuclear chemistry related things, personally, I have a lot of sources, primarily minerals. No, I don't have much radioactive stuff. What I do have right above me is my radium sample. I can show that to you in a minute. I have my technetium sample that I bought online, and I have about 5 minerals. See, I don't have that much. No. Do I have anything else that's radioactive? Trinitite, if you are counting that. So no, I also don't have to have a lot of. Yes, I have a technetium sample. I even made a video about that on YouTube, where I purchased that from OnyxMed. It was this really expensive one, and I analyzed it because OnyxMed didn't know how he was selling it, but without spectra. So there's no proof that it really was technetium, because technetium has this awful, really good property of not having any gamma lines and having a really low beta energy, meaning that he sells it in these very small glass ampules, and it's deposited on gold. So you have this strip of gold, and you have technetium electrochemically deposited on there, and this is all sealed in a glass vial. And outside of the glass vial, you pretty much do not measure anything. Like, not even with our contamination monitors, I couldn't even detect anything. So I was measuring the X-ray spectrum for like, I think, a weekend or 3 days. And after like 3 days of measurement, I could only detect faint levels of radiation, which I was then able to deduce that the sample that he was selling is actually technetium, because you couldn't normally just measure the radioactivity. And therefore, I now know, and everybody else knows, now OnyxMed also knows, that he's actually selling technetium and has proper laboratory proof that it's really technetium. It's the activity. Calculated that to be between 1,000 and 10,000 becquerels of technetium deposited in gold. It's all with a big arrow. Ugh. Do you have anything radioactive? Yes. It's a cool sample, but expensive, worth collectors with money to burn. Exactly. I wouldn't have bought it if I didn't have the YouTube channel. Of course, I'm a huge element collector. I love the periodic table, and I think let us analyze how much. So OnyxMed gave me a 50% discount for measuring a week, which is absolutely stupendously low, but I agreed to that. So I paid 350 euros for that, even though my time was a bit worth more. Cares. I made a cool video about that. So let's analyze how much money I got from making this video. So on the English channel, I got 7 euros from that. Great. And on the German channel, I think I got a bit more about that from that. So 7 euro. I mean, I had great fun doing that, and now I now have a technetium sample, which most people don't have. But yeah, I think I lost a couple $100 on that. I also made $7 from it. Wait, did I do that correctly? Oh. Yeah, so I think I earned like not even $20 from that. To be honest, I expected a bit more. I will look into the chat in a second. Give me. Yeah, I made $14 with that video and spending $350 on it. It's a great story to tell. The best ones I've made was buying uranium online. So I got a catch up. I wanted to show you the radium sample it's just radium paint from Nova Elements. Nothing special. Do I have my UV light? Yeah, 1 second. Here. And I recently bought a small ampule of tritium, these gas light things with HT gas in them. I don't have it with me right now because I borrowed it Advanced Tinkering because he wanted to use that for another video, and since they are pretty expensive, 20 euros, I figured I'd just mail him that for 80 cents. And that's it. So here's my radium sample. I love the Nova Element things. And it's encased in a glass ampule. As you can see, I just bought it like that. Cost me 20 euros, which is pretty expensive. Can you see? Yeah, you can see it. That's the only piece of radium that I have. Yeah. Oh, it's quite nice. I also don't need to have very active sources because every time I want to play with radioactivity. What? Oh. Did I left it in? I don't think I left that in. Showing me that you are going to see advertisement in 30 seconds, but I think yeah. Here we have the technetium sample. Technetium. And it's a very, very small ampule, very small even compared to the radium sample. Very tiny ampule, and you can't see anything because of the reflection. I don't think I can show you that even better. Oh, there is no way I'm going to show you. You have to watch the video. But in comparison, it's like Tinier than my thumb. 900? What? No, it cost me 350. Let me check on OnyxMap website. Went up? I hope not. No. 415. Did I spend 350? I'm not sure. I know I got 50 euros discount. There I said 50%. Maybe I did. I did. So, and I also have the Trinitite here. I didn't make a video about that because I'm a bit too scared that I'm going to leave out very interesting information that I don't know about them yet. Yeah, I'm not gonna destroy that. I would love to destroy that, but it would need hydrofluoric acid, and our LSC doesn't really like fluorides. So until I've figured a solution which I can add any more value than showing you just the gamma spectrum, because I would assume most of you have a gamma spectrum of the trinitide with the americium, cesium, europium lines, and I think that's it. You're not going to see much more of that, just because I don't have 50 grams of that stuff. I have 1 gram. Is it for 1 gram? 2.5 grams. Do you know if an average person can buy helium-3 in small amounts? Yes, I have helium-3. 1 minute. I have the helium-4. And I am trying my best to squeeze out this. Just going to take me hours. I have tweezers. But I also bought that from OnyxMap, but now they are sold out. So this is the helium-4, and this is the helium-3. It's very, very small. It cost me 30 euros. You can see the difference if you are exciting them with this little thing. I will definitely have to use this Tesla coil thing. Sometimes it works if it wants to, sometimes it doesn't. We can see something glowing. And I don't think you will be able to see a difference. It just glows slightly more violetish. Maybe, yeah. Not gonna see that on the camera. Just put that away. And 2 millisievert source. Yeah, no idea what that's going to be. Our neutron source has more than 20 millisieverts of gamma dose rate. Maybe a full ampule of cesium-137 chloride solution. Ours is empty, pretty much empty, and has nearly 1 millisievert. Oh, damn, I'm seeing stronger technetium sources that change the color of the glass. Fucking hell. And why is it in your bedroom? What, you mean the radium sample? If you're talking about the radium sample, it's encased in glass. And even sitting here from to there, I can't measure anything. So it's not leaking any radon or stuff like that. And even if I lüfte my room quite often. Ventilate. Radioactive finds with radioactive. I think I saw some of your videos, did I? Some canal. Yeah. Yeah, I really love the razorite. Yeah. And I didn't subscribe. Now I have subscribed. 50 euro discount. Got a good video out of it. Are you going to continue with the seminars now that the Discord is down? And if yes, where? Yeah, that's a good question. I am going to continue the seminars, of course. The I have some problems with the Discord server number 2, like the Red Zone 2, because every time I get there, which is not that often, I'm just reading toxic conversations, which I don't think I want to invite people on there. And if it doesn't resolve the problem of toxicity, I don't think I would be happy to present there. Of course, I'm going to. I want to keep continuing the seminars. Maybe it's not the Discord seminar. Maybe it's another platform. Actually, like the good thing about being on Discord is that the amount of stupid people joining is very low because you have to put in more effort to get to the seminar, which filters out a lot of stupid comments. Like if I just made a YouTube video uncut, and making them live is also a great way to interact with you guys. Not sure. See, all of the videos that come uploaded here on YouTube is just me rehearsing the seminar that I've held on Discord yet again for me personally, alone, and then editing actually and editing out all of these R's and M's since I'm not fluent in English, which makes the final video a bit easier to watch, right? And sometimes I can answer questions that were asked on Discord within the same video, and it's all just a natural flow of speech, which is quite nice. But of course, it delays the upload of the seminars. Most of the seminars are uploaded like 2, 3, 4 weeks after I originally presented them, because I want to keep them without these R's and M's. Get me? I could make them on YouTube Live. It's the same. Can just share my screen there. And sometimes I find mistakes in my slides, sometimes in my speech and stuff like that, and I can just rehearse them over and over again until they are free of any mistakes. But it costs a lot of time. And I don't have the time to open my own Discord server. Or if I did, I would have to have a team of moderators, which I will not be able to pay. And I won't bring any more value to it other than just me being there every Sunday, every other Sunday. No idea. I will continue them, but so far I haven't uploaded the seminar number 23 and 24, which were presented on the original Discord server. So I have some more videos to upload here on the channel without having to worry about that. Not gonna lie, I don't know where to present them again. That's on me to figure out. I don't have a satisfying solution for now. Oh yeah, 999 is Sonova Elements, but it's like 1 gram. Nine. that's not gram. It's the absolute exact same sample, but with a very small glass vial and a pretty sticker on it, which you can buy for 5 euros. And a markup of like 200% or something like that. It's insane. I bought pretty much every element. Not pretty much. Maybe 80% of my elements from OnyxMed, and I just bought the original glass vials from the manufacturer, and I bought the sheet of stickers from them, and I just stick them on myself. So I only bought those stickers from OnyxMed because I really like them. And the glass vials, I didn't bought them from them. I bought them from the manufacturer where they are getting them from for much cheaper. Yeah, and the elements from OnyxMed. So saved like, I didn't save that. I would have never spent that much money on my periodic table, which is already really damn expensive. But I will have to shop at Nova Elements again in the future because I really want to make a big video regarding the very fancy actinides that they are selling. So they have an actinium sample, a productinium sample, a neptunium sample, and I would really love to have these threes and analyze them to like the content of how much neptunium is in there. Is there really neptunium in there? In what chemical form are they in there? Yeah, I would really love to analyze them, but damn, they are expensive. I think they cost like what, all of them 3,000 euros. I will never earn that much money from YouTube for now. So okay, but it's when I have this money to spend that on YouTube videos, I will definitely buy them and analyze them for you and for me, of course. I want to keep them. I want a Neptunium sample. Anybody got the link of the new Discord for me? Yeah, I can send you that. I think I can post links and you can't, maybe, or maybe not. No idea. Would you destroy your Trinitite? I'm not sure. I have 2.5 grams of it. I would love to sacrifice half a gram of that. But I've calculated there's nothing of value that I could add from half a gram. I would have to dissolve like 50 grams of that stuff, or maybe 100 grams of that stuff, to even be close to considering pulling out some plutonium or stuff like that, because I don't trust the Neptunium guy who claimed that he has like berkelium and all the fancy transuranic elements in there. Of course, you use quite a shit out of them. And if I had that kind of trinitite, that amount, I would certainly try my best to isolate them. But yeah, in these small quantities, it's just not worth it. So sacrificing half a gram or none would add the exact same amount of value to it. So I'm just going to stick with not sacrificing any of that. Yeah. Yeah, he claims I think he isolated curium or californium, stuff like that, but I'm skeptical. Like the amounts of berkelium still present in this trinitite, and of course you never know where this trinitite was collected. So if here was where the bomb actually was exploded, the trinitite could be from right here with a very high amount of berkelium, but of course it could also be collected here. And then I would be sacrificing like 50 grams of this trinitite, which is still trinitite and cool collecting sample, just to get 0 berkelium from it. I have to work them chronologically. Are you still in the red zone? Not anymore. I have 2 days ago. YouTube app kind of sucks, especially on Android. Elaborate, please. I know. I just watch YouTube on my phone 24/7. What really bothers me is the amount of advertisement that is in there. It's so fucking much. It's like 40 seconds of ad just for one 2-minute video. What the fuck? I'm late, Rip, but here I can rewatch the stream. Oh, yeah, that's right. You could. I should make a thumbnail for that. Now we were just talking stuff. I don't know if I want to upload that. Maybe people will know that, oh yeah, that's Cage. He can make this mistakes live. Oh my god, my horrible English. Fucking hell. I would love to see cross-disciplinary equipment comparison, i.e. your counting setup used Geiger tube versus the... Okay, never heard about that. Dose calibrator. Ionization. Do you think that the gamma spectrometry is possible on usual CCD camera matrices? CCD camera matrix. I have no idea what you were talking about. I have to look that up. I think that's like common knowledge. CCD sensors. No idea. Absolute no idea about cameras. Looks like it could be possible. I know alpha spectrometry is possible on photodiodes, certain kind of. No idea about gamma spectrometer. I've built a alpha spectrometer, and I also built a beta gamma detector from scratch. I will definitely remake that video. I have this one. It was among the first nuclear chemistry videos that I posted on YouTube on the German channel. But since it's really my first video about nuclear chemistry there, where I built this 20 euro alpha spectrometer that works on air, which is part of my bachelor thesis, I would definitely wait to remake that video in German, and then I will translate the remade version on English. Yeah, I'm not going to remake the old version or translate the old version. It's just too horrible for you to see. Yeah. Have you ever worked with plutonium-239? Have I? Not worked. I didn't do any chemistry with it. We have a plutonium-239 calibration standard for our alpha spectrometer, which has like 800 becquerels of plutonium on it. Plutonium-239. There are some impurities of plutonium-238 on it, which you can see in the alpha spectrum. But actually doing chemistry with plutonium, I have never done. I know we have, I think it was 10 milligrams of plutonium oxide, and we also have like some becquerels of plutonium solution, which all basically just look like water, to be honest. As 100 becquerels, that's nothing. If it wouldn't stand there, you wouldn't be able to detect it unless you were using like a AMS, accelerated mass spectrometer. Yeah. It's very tiny white ampule. But I hope I could maybe ask someone. Like in November, there is a very big conference where every German nuclear chemist attends. Most of the very many nuclear chemists, and I know some people who are working with plutonium or who have worked with the plutonium that is available in Germany for chemistry. And maybe I can convince some of them to make a video about that. But of course, they are not going to be very happy about that. And the approval process for public, for making plutonium chemistry public is very strict nowadays. And sometimes it would take more than half a year to get this video approved. So if there is one person who is willing to do plutonium chemistry yet again, just for a video for me, willing to invite me into the lab of the JRC, I get to bring my camera inside of the lab, which are already all barriers that could potentially hinder the existence of plutonium chemistry videos on my channel. And then I would film everything. Of course, I would have to have them approved by the radiation protection officers and many more people most of the time. I would probably have to cut out some details like ventilation stuff, which I can't show when it comes to transuranium element research and stuff like that. And then the final version finally gets approved. But until the radiation protection officers and all of the other very important people are giving their okay to it, which could also take like 1 month, maybe 2, I don't know. Then maybe I can have them online on YouTube. So I've made a video about Cherenkov radiation on a German channel. And it's now sitting there for how long? It's not public. It won't be public for the next month. It's sitting there for, hey, where is it? When was it uploaded? 2 months ago. Yeah, it's sitting there for 2 months. Probably won't be released this year. Unless I get the approval of the person who was filming that. So the nuclear power plant, not research reactor operators. Yeah, and they just take that sweet time. Which, of course, they are busy. They have a job. It's not their job to approve my videos. So that you can kind of estimate how long it takes for me to, depending on where I filmed the videos, from first idea to actually filming it to making it public, takes anywhere between 2 weeks and 6 months. I've seen one guy attempt to make an I did Neptunium-239 chemistry, and the byproduct is plutonium-239, which is, of course, not measurable because it's so long-lived and it's not that much. But I did Neptunium-239 chemistry, so technically there was already a bit of plutonium being created in there. But that's a video that is going to be public. I will promise you that. Not this year, but it will come out eventually. Take a spectra, some old CCD sensor, got some spectrums and really. No idea about CCD cameras. I haven't seen that before, but yeah. Why is India and China still not using thorium for power? I know priming thorium is pretty hard, right? I'm not in the nuclear industry. Maybe they are trying to, but of course, there are certain difficulties with making a new power plant. For example, even if you know what you are doing, so even building like an existing, like a power plant, a nuclear power plant with existing like low enriched uranium fuel rods, like a trigger, it takes like what does it take? 100 months to build these reactors? It takes really long time, and that's if you know what you are doing. If you are trying to create an experimental thorium reactor, it would take much more time. So it might take you some decades to build up and to finally get the thorium or whatever reactor operating to a level where it's commercially available, and we know stuff like that. It's like building a nuclear power plant is really easy on paper, but fuck no. I have no idea about reactors. Currently studying a bit about reactor stuff, but Jesus Christ, it's the more you learn, the more you know that you have absolutely no idea what you were talking about. So I'm just going to ignore that question for now because I have no idea about nuclear reactors. If you don't like them on mobile, just use YouTube Relevance. Okay. Relevance. Huh. To melt down. Nope. No idea about dark matter. Please, everybody, like the stream. You can like a stream? That's interesting. Got a friend request. Yes. I hear that they are trying to make element number 119 and 120, and that they are pretty close from what I know. Just to give you some numbers when it comes to creating new elements. Yeah, we can talk about new element synthesis. Oh, yeah. Interesting. You can send me a link on Discord about that. So now I can talk about creating new elements, right? I did that on seminar number 24, which isn't published yet, and it was just off topic, but I'm happy to talk about more stuff. So, you have a nuclear reaction, right? Shall I talk this with a very German accent so that you are really thinking that you are learning? I'm just gonna leave that, which of course would make it easier. So, you have, when doing a nuclear reaction, you have your projectile, which hits the target, and then you have the ejectile. For example, we have our californium target, and you are accelerating calcium on it, and then you will have organesson from it, right? Of course, you can write them down in nuclear reaction equations. That was my cat in the background. Have you seen it? And since I want to give you some numbers on it, I will give you some numbers on it. It's really difficult because oh, it's on my laptop, I guess. Where's my laptop? Seriously, where's my laptop? Oh, it's in the kitchen. One sec, I will give you the numbers. Just look them up myself right now. So what you want is, of course, a lot of neutrons to shield the positive charge of the nuclides, because you are basically accelerating a charge of 20 plus to a charge of 98 plus to make 180. Of course, these charges will repel each other, and you would want to have a lot of neutrons to make this interaction very likely. I can't talk while researching on it. I really love that the organesson is classified as a noble gas, and it's absolutely like you couldn't be further from being a noble gas than organesson. It's not a noble gas. So where do we have the organesson paper? I know I have that searched. Think that's is that the one? No. I will leave my cat out for one minute. I just wanted to give you the numbers to make you think about how absurdly unlikely selentonite. No idea. I just know that copernicium is most likely to be a noble gas. Element 118. I'm searching for it. Searching. Just a proof point. It's stupid. Failed experiment. What was it? It was 10 to the power of way too many. Curium. Oh yeah, there we have it. So they used Californium 249 and calcium 48 projectiles. Took me way too long to figure that out. So calcium 48 is a double magic nucleus, but also so is the calcium 40, because you have 20 protons and 20 neutrons, which they are magic numbers, meaning that they will make a very stable nucleus. And you would want to have stable nuclei, of course, to make stuff that is somewhat stable. You would want to have all of your reactant, if you're talking in a chemical way, to be kind of stable. This is why they are using calcium 20. Yeah. Because even numbered nucleons will create a stable nucleus, and magic numbers are just a bit more stable, which of course they are going to be even numbers. And the number 28 is also a magic number for neutrons, and for protons should be as well, right? Yeah, it's a magic number. And with an excess of 8 more neutrons, you are still having this double magic nucleus, which is really stable, and you are having a more neutron excess to make this reaction happen. Of course, this is why they are using californium, because californium is element number 98. If you were to have element number 99, so Einsteinium, you would have to add one less proton to it. But if you were working with one proton less, you would have an uneven nucleus, which is less stable, and an uneven nucleus, which is also less stable. So you would have two very unstable target and projectiles, which would make this whole situation much better. And of course, Einsteinium is so short-lived that there were only a few experiments where they actually used Einsteinium as a target. They synthesized mendelevium out of Einsteinium, so they irradiated Einsteinium. I think it was 300,000 atoms of it with alpha particles, and then they got mendelevium, the first transactinide, if you wanted to. Of course, it's in the same row, but it has to be created not via N gamma and beta minus, but you will have to actually accelerate charged particles into it. And that was the first one to be synthesized that way. And yeah, Einsteinium is just very unstable. And californium, since it has at least an even number of protons, it's kind of stable. You can make a target out of it. And they were using californium targets. And they shot in, what was it? 10 to the power of 4.1. So this double magic nucleus times 4.1 times 10 to the power of 19 calcium ions to it, which is also very, very expensive to do, because calcium isn't that volatile. So you have to bring it into the gas phase to ionize it, and then accelerate it onto this. Of course, you are not going to accelerate calcium with a normal cyclotron. You would have to have a super heavy element accelerator like that. And out of that, 3 relation of a total beam loss. I think they got 2 events out of it, if I'm not mistaken. What performed? Yeah, at 2 projectiles. Spontaneous fission, total 3 decay chains observed. Picobarn. The cross section was in the picobarn range, which is close to nothing. And pretty much, I think they got like 2 or 3 organesson atoms from accelerating this many calcium atoms onto californium, which is absolutely insane. And if you are trying to come back to the original question, if you are trying to make element number 119 or element number 120, which, to be fair, most likely you are aiming to create element number 120, because 120 is an even number of proton, which would make it's a bit more stable. You would not use scandium, but you would want to use titanium for the same reason, because, well, you are looking at element number 20, calcium, and of course, you would likely want to keep your projectile and your target at the even number protons, and if you can, the even number neutrons, depending on what is more stable when it comes to the target. Since you can't increase the 98 californium, so element number 118 fermium, it's out. It's way too short-lived. You can't ship it. Of course, this whole synthesis thing broke down because Russia and USA just can't with each other. You would have to maybe do at another factory. They tried it at the GSI in Darmstadt. They were trying to make californium, and since these two add up to 118, and you can't increase this one, and this one is uneven, so it's also out. You would have to increase that, and if you want to increase that, you wouldn't use scandium, but you would just skip directly to element number 22, titanium. And this is really interesting because you could try your best to do titanium 50, because then you would have an even number of protons, which is quite stable, and you have 48 neutrons. And as I said on the previous slide, 28 neutrons is a double magic nuclear, is a magic nuclear number. So you would have some stability coming from the magic neutron number, and the even number of protons. So it's the next best thing than having calcium, because calcium as a target is out, since you can't go higher than element number 118. So this could, in theory, make, if you are accelerating titanium 50 onto californium, this could make element number 120, but since it doesn't have to be like a clean cut, it could also be that you are not just releasing like +5 neutrons or stuff like that. It could also be that you are having an 5NP reaction, leaving that some of these titanium atoms will not completely fuse, dumb word, to the californium, but they will, of course, will release some neutrons, but might be able that sometimes out of these 2 to 3 events after like 10 to the power of 19 atoms, some of it might create by accident element number 119. So it's best to just aim to produce more of the element number 120, and just to hope that some channels are occupied or some channels are reached with a XYZP reaction that would involve making element number 119 as a byproduct, rather than just sticking to element number 119. Of course, this one was tried at the GSI in Darmstadt, as far as I've heard, and it wasn't successful. But of course, since it took them 10 to the power of 19 calcium to produce like 2 atoms worth, imagine how many of these you would need to make 120. So a lot more of them. But of course, there are other. It's not the best one. It's the most logical one when you're coming from this one, in my opinion. But you could also just smash it. In the calendar Lisa, they were talking about, yeah, just use 2 uranium atoms. 92 plus 92, it's 184. There you go. And if they don't fuse, maybe they just split off and just a big thing sticks to another uranium atom. Maybe you get to element number 130. Who cares? If you have an accelerator that could accelerate uranium atoms onto uranium ions onto uranium target, go for it. But yeah, there are different ways to making new elements. So you don't have to stick with a very light projectile and a very heavy target. You could also change them a bit. But I am not nuclear physics-ish enough to know why they're using this kind of approach. Just wanted to give you a bit more insight into super heavy element synthesis. So this is not the only way. There are other many attempts to making super heavy elements. Depending on the nuclide that you want, you would also go with a uneven target. Like they even use like americium element number 95 to make certain elements. I think it was copernicium, rhodium, stuff like that. Yeah. Good night. Stuff like that. So I should read the chat more. Like the stream. Decently sized prototype of thorium reactor. Oh, interesting. This person. Yttrium 90. Okay. Guess you are just making that from strontium 90. Sounds fun. Make a video about that. Publish it, please. Potassium to organesson? How would you go about that? Did I write that here? No. Not sure what you mean. If you wanted to make it out of potassium, you would have to use element number 99, Einsteinium. Not gonna happen. It's just so short-lived. Yes. Should probably erase that. Otherwise, some nuclear physicists will kill me. These transactinides will get their own video. I promise that. It just takes me a lot of time to make videos. 0.5 picobar. Maximum cross-section for the Californium 249 calcium 48 reaction. Please let there be someone who wants to edit all of my R's and M's and mental farts out of the stream. To be honest, I'm really unsure what I'm going to. You can check Discord. I should check Discord. I have a message. Huh. Simon, did you know that the radio code is using your videos? Yes, I am selling them to I'm selling these videos to them. So it's official. Yeah. Especially creating them for them. So I'm filming them. I will try my best to match the color of the font from them, which they gave to me, because I said, that looks ugly if I'm using my own yellow and you have your yellow, a greenish tint. So I'm just going to adapt that to you. And yeah, they are even paying me to do these videos, which is where half of my income from YouTube comes from. Yeah, it's all official. Yet to get more payment from them. Thermite is fun. Yes, I did uranium thermite reaction 2 days ago in the lab. Wasn't really fun because the ventilation system broke because of me. So the reaction that I was trying to go for was this reaction. I had some, let's just say I had uranium tetrafluoride. Of course I didn't. I had the double salt, but it's still a uranium 4+ ion, and I reacted that with calcium to hopefully make the calcium fluoride and uranium metal, and it's kind of a thermite reaction since you have, well, you don't have oxygen, you have fluorine, and you have a very reactive metal. And this reaction creates a reaction temperature of around about 2000 degrees C. 2000 degrees C. And that was very exothermic and created a lot of fumes. And I did that by having a platinum crucible. And I had 600 milligrams of NaUF6 along with, I think it was 2.5 grams. 0.55 grams of calcium on it, metal beads, and then I had a graphite. So this is graphite, and then I sprinkled on some silicon dioxide. And this was then placed in the oven at 1100 degrees C, and it was very shit. Because I really wanted to have no air. This is why I topped it off with calcium, with a huge excess in calcium. And then I had the graphite because I was using the silicon dioxide to cover this one from air. So to protect it. And of course, at these high temperatures, I was worried that this one would just make a glass, and any uranium that was formed was just encased in glass if it reacted. So I used this graphite foil to shield air while protecting it from the silicon dioxide. And of course, these should react, and this huge access was to absorb any moisture and stuff like that. But what did it do? Just fucking exploded my platinum vessel, and I now have something which contains platinum and some uranium. Did it work? Absolutely no. But I can't seal ampoules in our lab because we can't have open fire. And we don't have the equipment to do that. I know it's very simple equipment. People at home do that, but a nuclear lab is just different from a home lab. So yes, I guess I would have to take my uranium hexafluoride, tetrafluoride, salt to the uranium lab where they actually have the right equipment to seal that in the glass ampule and put it back and hopefully get my uranium metal, because I really want to make uranium metal, but this didn't work at all. Of course, you could do the absolute same reaction by not having uranium tetrafluoride, but having uranium dioxide and react that with calcium to have calcium oxide. But I just have a lot of that stuff in the lab. So I'm just going to use that until hopefully it works. And if this works, I will use uranium dioxide powder to do that. But the uranium dioxide is a bit more expensive, so I'm just going to stick with the uranium fluorides, which there are videos about people doing that, and somehow I still don't get how I'm not able to do that. Yeah. Once I get that to work and I have a few shiny metal uranium bead in my hand, I can make a uranium thermite reaction with uranium dioxide and calcium. Should make a video like don't buy uranium on the internet, but with other sources. Like, the good stuff about this video is that we have cheap thorium nitrate now. But of course, I don't want to support these kinds of people. This is why you've never seen like a negative ion amulet or like a pen on my channel, because first, it's more money for these people who are scamming people. My professor is not happy because I don't want them at home. Why would I want them at home? And my professor also doesn't want to have these useless items in his lab. It's just more space taken up by useless stuff. And other people are buying them and making videos about them. I would leave this space for the people that don't have access to a nuclear lab. And I, of course, reach publicity-wise, it would be quite good stuff. Smarter, not harder. Thermite is fun. Did you? Yeah. Have you been problem with YouTube monetization? I was having issues with monetization at the start because of verification process. They didn't want to accept my personal license. I had to show them my driver's license for some reason. But now everything seems to go quite well. It's low, but I get the amount of money that I was promised by YouTube per view. Yes, it's a great collaboration. I now have this one sent by the company. I yet to find time to get into this thing, but I'm going to make a video out of it. But it will take me some time. My first impression, it's good. I think. I don't know why ever this detector. Neat gadget, to be honest. And yeah, it's a nice thing. It's just a brick. But it does it quite well, its job. I think it's maybe like the Android version of spectrometers, and the other one is the Apple version. The Radiocode is the Apple version. Like, this doesn't fit as easily into my pocket or anywhere compared to the Radiocode. But it's also a good device. Yeah. Uranium thermite is crazy. Is anyone even tempted? Well, corium, isn't it like encased in aluminum or steel? In my case, it's a bit more fancy. It's encased in platinum. This vessel costs 600 euros. I really have to do something special for my professor because I just wasted 2 of these. Maybe I can repair them, but now I first have to get this uranium shit out of this platinum alloy thing. And maybe I can solder it together. Are there any other Discords? Yes, I am on several Discord. I'm not that active, but I am on the German chemistry Discord, Chemielabor für jedermann. From Wheeler Scientific. Neat, but not active on Discord that much. That Chemist, Red Zone, Astrum, Radioverse, like the official Discord from Radiocode, and Red Zone 2, the sequel. Of course, Red Zone, the original one, is shut down. And Red Zone 2, the sequel, think it's the most used server by me, but also not that much. Yeah. Huh. Energy arbitrary units. Huh. Okay. Work smarter, not harder. We should make a video. Yeah. How extracting thorium from thorium tungsten rods. I think Wheeler Scientific already made that video. And I also don't have thorium rods. Like the welding rods. Yeah. There's I think Wheeler Scientific or someone else did that on YouTube before. And it's a neat video. You would have thorium dioxide. Of course, you can dissolve it in nitric acid and have actually a usable thorium compound. Of course, thorium dioxide is completely useless. I would love to make some more chemistry with our thorium metal rods. So just pure thorium, not anything with tungsten. Just don't have the time. Would love to. Like have all of the fission products separated by a hydroxide precipitation. So you know our big thorium metal rods, which are like this big. Just put them in nitric acid, like a bit, dissolve a bit. You would dissolve the whole rod part that is stuck inside of the concentrated nitric acid, and then you would have to precipitate the thorium with the hydroxide, sodium hydroxide, for example, quite exothermic. And then filter off the precipitate, which shouldn't be as active because it's just pure thorium 232, which is basically not radioactive in any practical senses. And the solution will have the radium, the polonium dissolved in it, and maybe you could extract the radium 228. And what else is there? Radium 228. There's another radium atom. You could maybe precipitate it as a sulfate out of it. That would be quite interesting to do. Yeah, 224 and 28. You would extract both of them as a sulfate precipitate. Yeah, that would be quite well to. Yeah, would be a neat experiment. I would love to extract minimal amounts of radium 226 out of pitch blender or uraninite, like on a scale of like 100 milligrams uraninite dissolved, and then have a barium sulfate carrier precipitation reaction, and maybe I get it to work to spectrometrically prove that I've separated out of the radium with the alpha spectrum, radium peak. Maybe I can get that to work, but not going to happen in the next few weeks because I am a teacher at a school, which takes up 99% of my time and my patience. So very little lab work is possible for the next 2 months. Unfortunately, yes. 10. I only see 7 people. Ooh, could you use the negative ion pen for extracting thorium and buy it from a person who wants to sell his pen? Selling these pens in Germany is illegal. This is why I shouldn't, like, if I were to do that, which I just don't like this idea, I shouldn't make this buying part public because it's illegal to sell these pens in Germany. So you shouldn't be able to get them. I don't know how Advanced Tinkering got them from Amazon. Clearly, some of the government people slept on these, and he was able to snap them. Maybe it was just a lucky coincidence. Who knows? Can the uranium be extracted with metallurgy? Mercury, uranium, platinum. That sounds like a wonderful combination. I have no idea about amalgams. Maybe platinum does it. Maybe mercury does it. Maybe uranium does it. Yeah, that's why I called this experiment a failure, because it's not elemental. So I'm not going to. I don't even know if I want to make this video public. ass video footage. And mercury and uranium. I don't think my prof is going to like that. Oh, the cat is screaming. Yeah, that's it. Because can you hear her? I think you can hear her, right? Why am I having the headphones off? Yeah, this is why. 1 second. Cats. Yeah, she really hates me. Oh, being picked up. It's a cat. Yeah. Have you actually heard the cat? Hardness test on pure thorium. And maybe scratching that with different elements? Maybe. Yeah, sure. This cat is. Now imagine that at like 5 a.m. You're not going to have much sleep. Yeah, maybe. She's a very old cat, so she forgets that I exist most of the time. Q&A with? Hi. It's warm in here. And cat, yeah. Cat is screaming in the background. Now she has stopped. Finally. Anything else? I don't think I have a video about my element collection, right? 1 second. Ta-da! This is the element collection. Of course, these ones are empty. Yeah, the actinides. But the lanthanides are full, except for promethium. Various other elements. That is an awesome collection. Yes, I'm really proud of it. I love looking at that. Makes me happy. It's missing a few elements. It's missing rhodium, fluorine, of course, liquid chlorine. I would love to make that in the university with a friend of mine in the uranium lab, because he's the kind of person that you would ask to make small liquid chlorine ampules. Maybe I can ask JJ Chemistry. Think he has some. Don't think he's going to let me borrow this. Promethium is missing, of course, and then yeah, polonium, acetine, radon, stuff like that. Numbers, yeah. Is there any isotope that you think are scarier than others? Isotopes. Tritium. That's really nasty stuff. But of course, as a T2 gas, tritium gas, it's really not that scary. But T2O, water, that's going to kill you pretty easily. So compared to normal hydrogen or deuterium, tritium is really nasty stuff. Any other isotopes, like compared to its same element? Of course, all of the radioactive ones, really scary, especially the ones that are very bioavailable, like cesium-137, which is really bioavailable. Any radium isotope, because they're very easy to get into your bones. Americium, same. Polonium, same. Yeah. I'm not quite sure how to answer that question. Oh, yeah, that's a good idea. Yeah, of course. That's how you would actually do that, but yeah, I have some fluoride here. I also have some more blue fluoride that I picked up. See? Doesn't show that. Is that this is kind of blue. But this one I collected myself in the Schwarzwald. Black Forest in Germany. Yeah. And some more samples. But of course my webcam is not good. So you have to wait for this video. The video about the fluoride search will come out on a German channel in 2 weeks. And then it will take me a bit too long to translate them into English. Yeah. But it's not, you shouldn't have like ordinary calcium fluoride or fluoride. You would have to have another variant of the fluoride called antozonite or antozonite, probably pronounced in English. This is the one that has actually been proven to have elemental fluorine in there. So this Chinese one, and the blue one, they contain yttrium and other trace elements. But the antozonite, which contains also a bit of uranium, these are the ones that would contain some elemental fluorine. So F2. This would be a proper placeholder, yeah. Like the decay heat of it, it's quite much. But of course, just normal water has a very high heat capacity, so I wouldn't expect it to bubble that much. It would just, most of the time, would just corrode the vessel that it's in. Because even though tritium is a very low energy beta emitter, even the low beta minus energy of tritium decay is several times the order of magnitude of a just normal chemical bond. So it would definitely ionize pretty much everything and would corrode through pretty much everything, as it's easy to break any bonds of any material that you would have it in. This is why, for example, you wouldn't use like Teflon to contain your tritium water, because it would just break the CF bond, leading to a production in HF gas, which is, of course, not something that you would want to have while having radioactive water. Yeah. So it wouldn't bubble from decay heat, as water has a very high heat capacity, but it would just corrode everything. Don't drink it. Most of the time, if you had one saying, if you spilled, I'm not sure about the amount. I have to look that up. You would die. It would kill you. Tritium water would kill you, definitely. Tritium gas, you should breathe it in, breathe it out. Sorry. That's it. Deuterium water tastes sweet compared to normal water, so in theory, I don't want to know that. I have some milliliters. I think I have 1 milliliter of deuterated water, D2O, heavy water. Not going to taste that. Thy lab did that already, so I'm not going to waste anything of my precious D2O. Are there any specials planned for like Christmas specials with some fancy chemistry? That would be awesome. Yes, we should make some Christmas specials. Can I add radioactivity to it? Is there anything Christmassy about chemistry? Making fake snow, but you're not going to involve anything radioactive into it. 122. Ugh. Organic chemistry. Bah. Auf Wiedersehen. Tschüss. Voice great. Heard a lot about season 137. I lived down in Sweden that got a lot of season from Chernobyl and my parents. Yeah. Yeah. I don't think it's iodine 131. Isn't that the radioactive one? I think it's the 127 that's the stable one, right? And you would want to swallow the non-radio. Yeah, 127. 131, it's the radioactive one that you are trying to block with just normal iodine. Christmas lights. I have questions. Ask questions. That's a good stuff to discuss. Christmas special for chemistry. I was thinking maybe uranium, isn't that like if you have like the ion exchange reaction, if you have a copper wire and you put that into silver nitrate solution, you will have silver needles forming onto the copper crystal, onto the copper wire. And if you form the copper wire in sort of like a tree way, it would maybe form like a needle Christmas tree. That would be quite fun. Of course, you can't do that with uranium because uranium won't be reduced in water as to its elemental form. You can make uranium dioxide powder in water if you electrolyze uranyl acetate at 5 volts for several hours at 80 degrees C. And when is it cisplatin synthesis coming? Yeah, 1 second. I will show you my screen. This I will hope I get it done next month on the German channel, and I would try my best to translate it. I won't make any promises, to be honest. It's just too much pressure for me. But I have finished writing the script for it. Where is the script? I can show you the script, but it's in German, so I don't think you can understand it. But I will show it anyways because I just wanted to prove that I have written it. Here. Share screen. This is what a typical script or video script looks like for me. So I write everything out and I just read them out on Audacity. That's it. So that's the final script. It would most likely make a 8-minute video. Yeah, most likely 8-minute video. So now I would translate that with ChatGPT and just read it out in English yet again. I'm curious if it had something to do with the neutrons. Taste, yeah. Taste and isotopes. That's a really interesting question. Gets down to how does matter interact with our taste buds and why does D2O taste differently? No idea. I would love to find it out. If any one of you knows stuff, tell me. If you have a video that explains that, also tell me. Interested? I haven't got to researching the topic because I am busy making other videos. So, can uranyl nitrate show photon emission by the radioactivity since it's fluorescent? Good question. Can it? Should. What? How would something like this come about? Radioluminescence. Maybe I can look that up. Radioluminescence. You know triboluminescence? Luminescence? Why is my camera shaking that much? Oh. No, it's not radioluminescence. It's an interesting question. I think this might be a really interesting topic regarding the fluorescence of uranyl nitrate, acetate, or nitrate, whatever. Yeah, I should make a video about that. Fluorescence of uranium compounds. Where do I write that down? Here. I definitely cleaned up my room quite well. It's my phone, if you're wondering what's vibrating. So what I would try to get like some grams of uranyl nitrate in our dark room, sit there for 15 minutes, and maybe I can see of it, because I was able to see alpha radiation, which was really interesting and really cool. And if any one of you gets to make that experiment, to be honest, I can't recommend that because it involves an open alpha emitter. But, so it involves this compound, zinc sulfide. It's the easiest. This fluorescent compound, right? The simplest scintillator. And I had some sticky tape and put that onto a batch of zinc sulfide, which the zinc sulfide stuck onto the sticky tape. And then I put that with the zinc sulfide side onto the alpha emitter. In our case, it was plutonium. And then I had a glass covering it up, so to not contaminate anything with the fluorescent dye, to be honest. And then I had a lens, and I was sitting in there for 50 minutes in the absolute dark. At some point, of course, this one does also a bit of phosphorescence. And after a while, you can see that. If your eyes adapt to the dark that well, you can see the phosphorescence of this compound. So it was glowing quite well visible. And if you then look through the lens, you can see every single alpha particle hitting the scintillator, causing the light emission. Light emission. So it was kind of like seeing a bag of yellow flea stands around, because all of the different alphas hit the scintillator and causing emission events. Really, really interesting. I wasn't able to film that because I don't think there's one camera that is able to capture that. Yeah, on a photo multiplier, should be, of course, but yeah, definitely. So chemistry science, yes. Any alpha emitter and any scintillator, if you have it dark enough, you will see some scintillation happening. Yes, but I think the question was if a uranyl nitrate crystal on its own, like a pure uranyl nitrate crystal, could glow, because maybe it also does do some scintillation. That would be quite interesting. Yeah. I was using our 800 becquerel plutonium source for that. So just to give you some numbers. How do electromagnetic rays lose energy? By that, I'm asking if I take, for example, 5mm thick lead and cesium and place it next to the spectrometer, would the Yes and no. So you will see a spectrum that looks something. If you were to have a gamma emitter, so you have your radioactive source. This spectrum would look something like this if you have the counts. It's a really common exam question. It should look something like this, where we have here the full energy peak at 661 kV. Then you have the Compton edge. And then you have the back scattering. Because most of the time, a electromagnetic wave, for example, our 661 kiloelectron volt line, loses its energy by interaction with electrons. So what could happen let's say this detector is open, so there's no material, no interaction within the detector for now, it could lose some of its energy to the lead atoms. Of course, not it's because like the electrons occupy that much more space. It's highly likely that they will interact with the electrons, and either they do a photoelectric effect, so the whole energy of the photon is transferred to the electron, and the electron shoots out and ionizes the lead. Of course, then this gamma photon that does photo effect, PE, photoelectric effect, would not come through, but an electron would be shot out, depending on how thick it is. And it could also be scattered, so Compton scattering, meaning that you would have an interaction of a gamma photon onto an electron, then you have a scattered electron, and by definition, the now scattered Compton is another Compton scattered photon is another photon, but let's just say it's the same. It would lose some sort of energy, so we have 100% of the energy of the gamma photon, and let's say 80% of the energy comes to the electron and 20% comes to the one. And this Compton scattered one could then be detected, of course, with 20% of the energy, meaning that this would be somewhere around here, backscattering. Because then this one would do a photoelectric effect within the electrons of the detector, and then the electrons would have 100% of this 20% of the energy and could then be detected and be converted into signals, and then would come out like this because this amount of energy was deposited in there, not that much. Of course, this gamma photon could also not do this interaction and do this interaction, photoelectric interaction with the electrons in the detector, leading to a photoelectric effect in the detector crystal with the electrons there. And the electrons would now 100% of the 661 kiloelectron volts would be detected here and would lead to a signal here, photo peak. And could also be that this whole thing happens within the detector, and the detector actually doesn't directly measure the gamma photons, but it measures the electron that are knocked out by the gamma photons. And when this happens, this one would be measured by the electron and not would happen inside of the lead foil, therefore leading to having 80% of the energy deposited inside of the detector, and this one would maybe scatter out. Another one. And this would lead to the Compton edge. Of course, there is a certain difference in energy, which the photo effect, which the photon can't lose to an electron without either just doing photoelectric effect, or let's say, for example, it would lose like, let's say 99% of the energy. I would be left with 1% of the energy. This 1% gamma photon would quickly interact with another electron because, well, it's a detector. There are more than one electron in the whole detector. And it would also deposit this last percent onto this electron. And these events happen so fast that the detector can't differentiate between both and would just put all of this scattering stuff, which should be here. But this happens so fast, so it would just put the signal here back into the photo peak, leading to, well, yet another photo peak. Physicists will kill me now. How did we even get to know there is ortho and para hydrogen? I know I should know this answer, but I don't know the answer. They have, oh my god, I've been to a tritium lab and they have explained that to me so well, and I know I have it on camera, but I don't know out of the top of my head. I'm sorry. So I will answer this question when I make the tritium video. Okay. If I add uranyl nitrate on a photomultiplier in the darkness, yes, it will show the signal. I have answered that already. Uranium does not produce enough radiation for the light to show up. Should be. I only used 800 becquerels of plutonium. It's not that much. And I think you can have 800 becquerels of uranium. If you have like 1,000 becquerels of uranium, should still be visible. Maybe I do that experiment on my own. But yeah, I know what you're saying. But I guess if you're trying hard enough, you could get the fluorescence on it. Otherwise, yeah, I think you should be able to see that. But not even a single. If you do photo counting, for example, but not even a. Thank you. Uranium does not produce. Maybe. Yeah, I love fluorescence. Green color is nice. Could radiation mess with different storage medium like microSD? No. Yes, but no. Theoretically, yes. We have our 30 millicurie americium 241 source, and I've placed a USB stick on it for a month, I guess. I was just doing fine. There was nothing. And this thing has a contact dose rate of more than 20 millisieverts. So unless you are throwing that into a reactor, which the operators won't let you do, there's no way radiation will ever affect any electronics. No. Impractical. No. No, there's no video about that. just for shits and giggles. We also put some pumpkin seeds on them and tried to cause mutation, but didn't work. Not at all. We also did a petri dish on it to see if it would affect mold growth. Nope, not in the slightest bit. So I just left that out. I didn't make a video out of it. Did you try? Oh, my professor would read this and would fucking kill me. I think I brought that up for like 100 times to him. Yeah, I was trying bacteria. Yeah, petri dish, and we were trying to grow whatever was flying in the air, and it wasn't affected by that. So the amount of radon. So, should we calculate that? Maybe. Yeah, let's calculate that. For example, I will calculate it the very difficult way. So stick with me. Let's say we have 1 gram of radium 226, which is not going to happen anywhere soon, anytime soon. Yeah. The most we can manage to get is like 3 milligrams. It's visible, but not 1 gram. But this 1 gram has an activity of. Should we do Curies? No, we should. 37 gigabecquerels. So in radioactive equilibrium, that means we have 37 gigabecquerels of radon 222, which is equivalent to a mass of, let's top browser up. Radon has a specific activity. Radon 222 has a specific activity of 569.32 times giga 10 to the power of 4 gigabecquerels per gram. Dividing stuff. So 37 divided by 5.6932 times 10 to the power of, was it 4? Oh, sorry, it's 6. 6, 10 to the power of 6. That would equate to having 0.000000694 grams. Okay, so not that much. Okay, let's divide that by the mass of 222. This would mean divided by the molar mass of 222 grams per mole, which would equate to, yeah, sorry, any mathematicians out there, you are going to hate me. 10 to the power of minus 6 mole, which using ideal gas, you have 24 liters per mole. And you have times 24 liters per mole would leave you with 7.02 times 10 to the power of minus 7 liters. So 7.02 times 10 to the power of minus 4 milliliters. Microliters. You wouldn't even have one microliters of radon gas from 1 gram of radium. Meaning, good luck having this in your ampule. And best of all, this would constantly, after a month, you will have this amount. Of course, there would be a constant supply of helium because of alpha decays, right? You have one alpha particle, and this would also decay into polonium, which would also decay, releasing alpha. So you have a 3-to-1 ratio of helium to radon, meaning that you would have pretty much non-radon and a lot of helium. And of course, the emission spectrum would just visibly be basically purely helium. Of course, if you do a spectrometer, if you use a spectrometer and you analyze the emission spectrum, you might be able to see the radon lines, but this would involve 1 gram of, and we would only be able to have a thousands of that. So a thousands of that. Not going to be able to do that in the lab. So you can did some radon air from our uranium blue barrel, and I put that into our cloud chamber, which was really nice, but I'm not going to be able to get a emission spectrum out of it. Just to give you a sense on how little radon gas is produced in even a big amount of radium. Yeah. I don't remember that video. What about bacteria and viruses? But how come electronics in outer space? Well, the radiation exposure in outer space is absurdly high. It's really high. And of course, the energies of these radiation, it's just insane. Like our what is americium source has alpha particles at 5 point something mega electron, 5.4 mega electron volts, and these ones in outer space, they have like giga electron volts sometimes, depending on the particles, and several mega electron volts. So it's really different energies, different amounts, way longer because they will stick in outer space for like several months, and I just tried 1 month. How much neon is in a bulb? I have no idea. Feel free to research that on your own. Mhm. Hmm. What's your favorite isotope? Technetium 99 is quite awesome because this is how I got into nuclear chemistry. But I also loved neptunium. And of course, the most stable one, neptunium 237, which is the most available one because you can actually do some chemistry. And I really love neptunium chemistry. It's so colorful, that makes it quite awesome. Of course, plutonium was also interesting. So many different isotopes. I really don't like cobalt 60. Strontium 90. Not my thing. Polonium 210 is like pretty much my breakthrough when it comes to nuclear chemistry because I was able to freeze my experiment with extracting polonium 210, which is, I think, the only achievement that I've done on my own when it comes to nuclear chemistry, creating that experiment. Of course, all of the other very interesting isotopes like astatine 211, 211 is really interesting. Radon 219, I have a video planned with that. Francium, my arch nemesis. Radium's it's okay. Actinium is also quite interesting. There's so many interesting elements, and I can't pick a favorite isotope. Of course, most of the time it's going to be the most stable one because it allows me to do some actual chemistry with it. Also, tritium is nice. Can't decide. Really can't decide. Yeah, I could just go on and list several elements in its special isotopes, but there is no way I'm going to choose an element. An isotope. Technetium and neptunium. These are my favorite elements. That's pretty much the hardest questions. The hardest question. I'm going to ask that all the nuclear chemists on the conference there. Yeah, it feels so mainstream. Yeah, every time I hear someone talk about isotopes, yes. Sometimes season 137, but it's actually cool because you can actually use it. You know, like we have a good amount of season 137 our lab, which you can do experiments on. It's really a great nuclide to teach people about radiation because you can use it as a beta emitter. You can use it to teach isomeric transitions. You can just use it as a pure gamma source if you just shield it with aluminium and have a pure stream of just one energy. Gamma radiation is 661. This is why it's just impossible to do with cobalt. Cobalt is toxic. It has 2 gamma lines, which of course makes it a bit better for calibrations, but for experiments, from simple demonstration and teaching experiments, you would want to have a just 1 gamma line cesium. Of course, technically that's not true. Cesium has another gamma line in a very low energy range, but who cares about that? And cesium is a great isotope when it comes to teaching stuff. Cobalt, it's not. I don't like cobalt. I think it's the barium 137M generator experiment, where you wait for your cesium 137 to decay to produce some barium, which of course will decay into barium 137G. But if you are working quick, you can, with a carrier of barium, you can extract barium 137M out of a solution of cesium 137 and then measure its decay. And then after 20 minutes, you will have the barium 137G. But it's pretty much the only experiment that is feasible in a nuclear chemistry lab where you can extract a metastable isotope. Of course, there are many other metastable isotopes that are quite long-lived, but I think it's quite neat that you could say that you have a sample with barium 137M for 20 minutes with a very high concentration of barium 137M, and of course the natural carrier barium, but pretty much a negligible amount of barium 137G. So that's quite an interesting experiment. Maybe you can make a generator experiment out of it, but without an ion exchanger, that's going to be very difficult. Who knows? Maybe you can do it. Yeah, I like that experiment. Hmm. 2 hours and 12 minutes strong. If I had like a better camera, I would love to show you my elements, but I think that's stuff for a video, which I just want more hours in a day to make more videos. Really love making more videos. What about disk sources? They are not that common in Germany. We have these small rectangles from Eckert and Ziegler, but disk sources, they are not that common in Germany. There are really interesting ones for collectors and stuff like that. I would also really love for just private people in Germany to have as easy access to radionuclides as you have in USA, even though they are really expensive. But I mean, there should be some cost associated with having radionuclides at home. Of course, they shouldn't be very active, but they should be active enough to do some simple experiments, understanding radioactivity a bit more. And yeah, I would love to have these disk sources with like 10 microcuries of radionuclides on them to do experiments at home. So, because in Germany, people are quite literally, if you want to do nuclear chemistry, either you are young enough to study chemistry and maybe you have a nuclear chemistry lab in your area. You can then do experiments there, which of course is going to involve a lot of time. But if you want to do some easy experiments at home, you're pretty much forced to break the law and extract uranium and do messy stuff, which just let them buy that stuff. Right? Maybe write their name and keep track of how much they have bought. Yeah. Oh, maybe I can show you some. Later. Let's see. Oh yeah. Isn't that lovely? Maybe in front of my t-shirt. Yeah. That's cool, right? That's nitrogen, N2. Most beautiful color. No. Could rant about German education system when it comes to chemistry in schools, in high schools, because I'm just at the moment teaching in high schools, but I'm not going to become a teacher. I will never become a teacher for high schools in Germany unless something drastically changes when it comes to how teaching is forced to be that way. You have some freedom as a teacher. You can do experiments depending on how creative you are. But like the way the topics that students in Germany are required to learn them, like the order of topics they are required to learn them in, it's absolutely stupid. And I'm not going to teach this order because there's no one who actually knows how to teach chemistry would approve that. And since I can't teach it that way because I'm not allowed to, I have requirements that I would be able to obey. Yeah, obey. I just can't teach it that way. You are just basically forced to do confusing chemistry lessons, which is a shame. So unless I can change some topics from this year to the next year, and otherwise, I'm not going to teach it. It's a shame. But studying nuclear chemistry, even in Germany, even after they left nuclear power, still an ongoing topic because radionuclides, you will have to use radionuclides for pretty much how long society lasts. Quite a long time. Radiopharmaceuticals, other sciencey stuff. It's not just restricted to nuclear power. As many people think, if I tell them, I do nuclear chemistry videos, is there like no future in there in Germany? There is enough future. Like research, more research, application, nuclear medicine, stuff like that. Analytics, enough to do. More research. You haven't worked with, but really like to work with. Yes, we have Protactinium 231. We have 5 milligrams of the oxide, and I would love to do anything with that because my goal is to not leave university until I have experimented with the first 92, maybe 94 elements. And yeah, Protactinium is very high on there because I know we have it, but we just, at the moment, we don't have the right instrumentation and the right space to work with it safely. We just have enough space to store it safely, but we can't work with it. So it's really high there on the list because not even many nuclear labs have access to this amount of Protactinium, and we have it. So I'm really, really excited to maybe someday work with the Protactinium. But of course, there's a lot of work that is involved with Protactinium chemistry. So I think I have quite high chances of getting to experiment with most of the elements. I mean, I have ticked off some of the exotic ones, and some of the most common ones I have just yet to tick off my list, like arsenic. I've never worked with arsenic, but I can say I've worked with fluorine, the elemental stuff, and the fluoride. In this case, I wouldn't care, to be honest. Yeah, with the noble gases, I mean, I have them here. I can do the emission spectrum, and that's enough for me. I've worked with technetium. Most people won't. I have yet to experiment with elemental cesium. I know I have used cesium salts, rubidium salts, and stuff like that. Yet to work with the noble metals, which is quite easy to do. Some more interesting stuff that I've worked with. Some of the lantanides I'm missing, but that would be quite easy to do because they are quite common. Yeah, we have promethium there. I've measured it. I didn't do chemistry in the practical sense with it. Maybe I can convince my professor to do some small promethium experiment, just so I can say I have worked with promethium. Um, After this, rare elements. Yeah, iridium going to be expensive. I did mercury chemistry. I did mercury cyanide chemistry. I did radioactive thallium chemistry. So this is something not many people did. I never worked with the stable thallium, but I worked with radioactive thallium. Interesting. I did polonium chemistry. I know some people who do acetine chemistry, so this is interesting to do. I did, in a sense, I did radon chemistry. Not really radon chemistry, but I extracted the daughters of all of the radon daughters, like the radon 220, 222, 219. I extracted the daughters, so I would take off that radon. I did radon. I never did francium, going to be my arch nemesis, but I mean, maybe in the future I can. For this, I don't have to do any chemistry. I just want a spectrum where I can see the gamma lines of any type of decay from francium that I know I had francium in there. This would be way than enough for me. I tried so many times to get a francium spectrum, never worked. Radium chemistry, carrier. I extracted radium from Brazil nuts. Think that counts. Actinium, quite difficult. Thorium, I did thorium chemistry quite a lot. Protactinium, again, I did the Protactinium 234M generator experiment, but I really want to do some actual Protactinium chemistry with Protactinium 231. Uranium chemistry, I did a lot. I did Neptunium chemistry, Neptunium 239. I would love to do a research module in Dresden to work with the 37 isotope, to do like some really cool carrier-free Neptunium chemistry. Maybe I get to work with plutonium chemistry. That would be really cool to take off every element from element number 1 to 94. That would be really interesting. Yeah, and for anything else, difficult to organize. Yeah, if I can, yeah. Protactinium, arsenic sounds a little scary. Yeah. Protactinium is really nasty stuff. Protactinium is on a gram to gram base. It's less toxic than polonium, but on a becquerel per becquerel, it's more toxic than polonium. So 1 becquerel of protactinium would harm you more than 1 becquerel of protactinium 231 would harm you more than polonium 210. Of course, 1 becquerel of protactinium 231 would be a larger sample in terms of volume and mass, but from the activity point, protactinium is more toxic than polonium. Yeah, americium chemistry, right? Even organizing plutonium chemistry, I've never seen plutonium chemistry being done. So even organizing that would be quite difficult. And if I can get that, maybe then I can, try to organize my way to americium chemistry. But I would also love that to make chemistry with all of the elements, or maybe like film super heavy element research. Of course, chemistry can only be done with up to hassium. Hassium chemistry has been done, so the hassium tetroxide has been characterized. But filming that, it's just mostly computer work. Up to California, we can actually see the crystals, but like working with transuranic elements, quite complicated stuff to organize, to get the for americium and stuff like that. You really have to do like write a research proposal. Why is the chemistry that you want to do with that element important? You have to practice that experiment with all of the other, with the lanthanides. So if you want to do americium chemistry, you have to practice that with cerium. Do the same experiment with cerium several times. And if you really know what you're doing, then finally, after months of training, you get to actually work with americium. So it's quite complicated to do stuff like that. For uranium and thorium, you don't have to practice that with the lanthanides, but yeah, you would have to practice the experiment of everything past uranium with a corresponding lanthanide. Maybe with neptunium and plutonium you don't have to. I'm not that deep into nuclear chemistry yet. Even with technetium, you have to practice with rhenium first. So I did a lot of rhenium chemistry. Yeah. Maybe I should. Well, looking forward to platinum. Yes. Yeah, to say that you've worked with plutonium is really high confidence, but it must be hard. Yes. Yes, the security. And like getting your hands on plutonium, difficult. And of course, since kind of my whole unique selling point is me making videos about it, being able to convince someone that not only can you do the video, but you can also film and publish that, difficult stuff. And to be honest, most of the best videos are when I just get to watch the other person do the chemistry. So if I really want to make like a visually interesting video, I don't do anything of the chemistry. Sometimes I assist, but most of the time I just stand behind the person and film them over the shoulder, and they have to do their best to not be nervous and shake all of that. Because I filmed in Mainz at the reactor, and people was like, "Really? That's so different when someone is actually filming your hands and stuff." I'm not even filming like the person's face or something like that, but even filming the hands, they were like, "Oh, fuck, I'm nervous. I forgot how to chemistry again." Like, just do chemistry, and they're like, "I can't. You're filming me." It's so visually, most interesting videos would be to me filming and not doing the chemistry, but of course, sometimes I want to do the chemistry, and that would then the video would suffer a bit. Yeah, it really depends. Like in a glove box, it would be like plutonium. You are not going to handle outside of a glove box. So when it comes to plutonium chemistry, it's most likely me just slapping my phone onto the glove box and directing the other person to just hold that to the camera. And he was like in the glove box working. Have you ever worked in the glove box? If you didn't, it's just big acrylic thing with these two big gloves that go in like this, and you're just working there like an astronaut in this inert atmosphere, and everything is more difficult. And then doing something with radioactivity, and then doing it so that the video is awesome, because I can only hold my video here and maybe there and stuff like there. And if I have it at an angle, it would reflect and would look shitty on the video. So yeah, and then me doing this stuff while having the tripod in front of me and filming, that would make for a very awful video. I did a video like that. I'm not going to publish it. I was trying to make uranium tetrachloride, and the video footage was absolute ass. So I'm just going to repeat the whole video again, because the video footage is do I have video footage? No, I know I have it on my computer, but it just looks awful. Where is it? Is it here? Tetrachloride. In hot cell? No, I haven't worked with a hot cell. No, I saw one, but I don't have the necessary training to be led onto a hot cell, so that's not gonna happen here. Wait. Oh, we have. Yeah. This is how an experiment would look like if I were the person filming and doing the chemistry in a glove box. I know this glove box looks absolutely ass. It's messy, stuff like that. This is why it's not published. But this is just me weighing out anhydrous aluminum chloride. Do you want to watch this kind of video? I won't. No. We should stop that. That just looks horrible. So this, you get the point why I'm not doing videos like this. It just looks so boring. Not good. Manipulators. I was allowed to use a analog manipulator, like this grabbing thing. Not in a hot cell, but kind of a hot cell. It wasn't hot, so it was just to train, just putting on some wooden bricks and just was stacking them up. That's it. That's all. I never got to work with chemicals in this roboty thing. Great video for behind the scenes channel or blooper channel. Yeah, the thing about bloopers, it's sometimes just not. The problem is I don't want. Yeah, of course. Yeah. I'm trying my best to show adequate safety precautions and how to do chemistry. Like, I don't want to people. I don't want to show people that I do stuff too casual. So sometimes not putting on gloves, or sometimes not putting on the right gloves, like the acid resistant gloves and stuff like that. Sometimes I do that because it's just way quicker, but I don't want to show that on video. So not that people would think I would advise them to do stuff the way I do. I'm not a role model 100% of the time, and especially when it comes to radioactivity. Sometimes I film stuff that goes wrong and it shouldn't go wrong, but it still does. And of course, since I'm filming everything, I have video footage like this. You see where the moral comes into play. No. Could a fuel rocket ever fall into someone's pocket like in Simpson? Nope. I saw a replica of a trigger fuel rod, and these things are like this big. Like, even cutting out the whole situation, like how would it go out of the reactor with the 6 to several meters of water above it and accidentally, like there should be at some point it should be a situation where this whole scenario would stop, but even fitting this thing in your pocket would be impossible. Yeah, I'm a nuclear criticality safety analyst from the States. Saw this stream earlier while I was driving. Got any question for someone in the industry over here? What does a nuclear criticality person do on a given day? Like, I've seen in Switzerland some nuclear power plant operators there. To be honest, this job really looks really boring. You're just looking at panels and hope that nothing goes wrong, which 99.99999% of the time it doesn't, and you're just sitting there and waiting. Is it like I feel that the learning process to becoming one is really interesting, and the actual job itself? Do you do exciting stuff? In Simpson, he had a drop and run cobalt rod. Like a nuclear fuel rod, these things are really big. And this was just a trigger one, so a research reactor. Of course, the actual for nuclear power plants, not research reactors, it's just up there. So they can work with fissile material without accident hearing. No. What kind of experiments? Like neutron experiments? Fissile material. So a lot of neutron computation stuff. Okay. System reactivity. Yeah, I know that. Okay. So you really have to have a thing for numbers and physics and maths. because nuclear chemistry is mostly just chemistry with spicy elements, and chemistry can be really interesting because something happens and physics experiments. Yeah, production of new fuel actually sounds really interesting. Defense application, yes, all neutrons, transport equations. Oh, interesting. Yeah, I haven't watched Simpsons too much. It emits really high energy gamma radiation and also very low beta radiation. It's really interesting element because like it's one of the few elements where the Q value for the beta decay doesn't actually result in the actual beta particle, the electron emitted, having most of the energy, and just the excited daughter nucleus having the rest of the gamma energy, which is just a fraction of the whole Q value for this whole decay. But it's quite the opposite. So the electron itself has a really low energy, and most of the decay energy is released in the form of high energy gamma radiation at the 1100 line and the 1300 line. So it's really interesting that most of the decay energy is released in the form of electromagnetic radiation, gamma radiation, and not in the form of the actual beta radiation itself. This is because quantum mechanics and stuff. Actinide chemistry and stuff like that. Oh, yeah, that seems interesting. Saying experimentalist wants to work with. Okay. Yeah. I see now. That really sounds interesting, to be honest. I don't want to see the safety protocol for someone justifying. Yeah, I can't do that with like half a gram. I need half a kilogram of that. And like the justification for upscaling it like 100 times more. I would love to see that protocol. It's like an essay of pages. Yeah. Cobalt 60 actually is a better minus emitter. But the better energy, the better decay results in more energy release in the form of gamma radiation and not the beta particle itself. You could look at the decay scheme, should look really complicated. I know there are two energy levels that have to be went through. So you have one gamma line, and then because you have one reach, I'm just going to show you. Fucking demonetized. NDS web. Where do I have it? I think I have it linked in the Technism video. No, I haven't. Where is the video? So let's see the decay. I can share my screen now. There we have it. Should go back a bit. Access the database. And then where is cobalt? It's quite a light element. nickel, cobalt, not cobalt 61, cobalt 60. Cobalt 60, the gammas, a lot of gammas, and then where is the ground states and isomers? Levels, I think it's the levels. A lot of levels. Should use that a bit more. Scheme. Yeah, decay scheme. Well fucking done. So. Oh no. It decays into nickel 60. I should probably see the. Ooh. What happens here? What is... I know how to look that up in the lab on the book, but at the moment I'm kind of stupid, I guess. Decay radiation. Ah, here we have it. God damn it. So we have the cobalt 60 in the +5, which could then decay 99% of the time into the +4, which makes sense because the delta J is 1, which is quantum mechanically allowed. The ground state has a spin of 0, which means that a direct decay from the +5 into +0 is heavily forbidden, meaning that this decay will definitely result in the formation of gamma quantum, because the decay into the ground state is quantum mechanically forbidden. And yeah, a very high energy state with this amount of energy is produced via this decay. So it would mean that the decay energy is in this difference around 300 kiloelectron volts. Beta radiation, 300 kilovolts. See, to populate this excited nucleus of the nickel 60, and this would then de-excite while emitting this line, or emitting this 1171, so the first gamma line of our cobalt 60, which would then decay into the +2 state, and then from the +2 we have the first gamma emission, and then from the +2 into the ground state you have this transition with the 1332 kiloelectron volt line. So this is where the two lines of the cobalt 60 decays come from. So a decay into the ground state is quantum mechanically forbidden because of spin, nuclear spin. But the decay into the excited state with the nuclear spin of +4 is quantum mechanically allowed, or less forbidden. I'm not quite sure how it's without a change in parity. I think with change in parity it would be allowed, and without change it's just less forbidden. Would have to look that up. But this can do via beta minus decay. And then we have the excited state that de-excite. Of course, it could just completely go from the beta decay excited state directly into the ground state, emitting this 2500 one, but the occurrence probability is 10 to the power of -6%. Not going to happen. Of all decays, sorry. And then we have the occurrence probability of nearly 100%. And then yet another 100%, because, well, if this one is reached, you can only reach the ground state by the emission of this one. But of course, it could not only go into the second, this +2 state, but it could also go into the other +2 state with this emission, meaning that this would be subtracted from the 100. So many different levels that could be occupied by the de-excitation of the nickel-60 nucleus. But the most common ones are the de-excitation from this level and then directly into this level. With 2 occurrence probabilities of nearly 100%. So the cobalt-60 is kind of a low energy beta emitter with 300 kiloelectron volts and really high gamma emitter. Yeah, Mike, make a YouTube video. I think after nearly 3 hours, we can stop the stream. I think that's the longest stream I didn't plan. Most of the seminars are like 1 hour, but you guys were asking really interesting questions. Got me to talk a bit. So, not quite sure how long I will leave. Can you convert kiloelectron volts into rads? No. Bring back the cat, please. No, she's sleeping on the couch. What was rads? Rads. Not using freedom units that much. Isn't it like a Röntgen? Radiation unit. Joule per kilogram. In SI units, it's gray. So no, you can't. Unless you know the matter that it's emitting into and the type of radiation, not easily converted. Sieverts, becquerel. That's it. No other units. Biological stuff, actual physical stuff. Anything else in between, I don't care. I don't use. Yeah, gray makes sense because it's physical stuff that you could measure, but there's no application for me in the lab. Even Sieverts, most of the time we just know how hot stuff is. We really do not care if a sample has 120 microsieverts an hour or 150 microsieverts an hour. It's just, okay, it's in the 100-ish. So just don't lick it. If it's in a millisievert or like 500 microsieverts, in our lab, we consider that to be quite hot. If it's in the millisievert range, we tend to build a lead wall in front of it. Yeah. In other labs, I've seen people say to a 1 millisievert tellurium target, oh, that's quite not hot. We should irradiate that more to get it a bit more hot. So it depends on where you work. So I think, unless you have an urgent question, you can also always write me on Instagram. I don't have a live. I will answer you quite fast. And yeah, I'm not quite sure how long the live stream will stay uploaded. If it does so automatically, I don't know. Microcuries. Yeah, you can convert becquerels into microcuries, but I love to do becquerel. Yeah, not microcuries. Sometimes the manufacturer uses microcuries and curies. Can you convert microsieverts into... No, you can't. You would have to know the distance of the source to the body that is getting the radiation damage, which is... No. You would have to know the type of radiation, so you'd have to know the radionuclides, because microcuries is the amount of radionuclides that you have. Microcuries is the amount of decays that you have indirectly of your radionuclides. Of course, depending on the radionuclides, this or that energy would would be more or less harmful. If you have a pure alpha emitter, the microcuries convert into sieverts would be close to 0 sieverts, because alpha radiation after 5 centimeters, if you account for the distance, would be like equivalent to 0. If you have a really high energy gamma emitter, depending on how high, because some of the high energies would just go right through you. So there's a sweet spot of not enough, not too much, not too little energy that would deposit all of its energy perfectly in your body. And of course, converting to like the actual physical stuff, becquerel or curies, into the biological damage, it's such a complicated type of calculation, because like even with the laws that involves how much microsieverts have you received, all of these limits on how much you can receive are very conservative when it comes to health risk, and all of the measurement devices are really conservative, because you would always want to be on the safe side rather than on the sorry side of things. But yes, if depends on what you're measuring, of course, it really complicated stuff. Yeah, but I did that, the Red Pro calculator, and I compared it to our official dose rate monitor. The readings were off by like 30%, because, well, our devices are calibrated with a certain source, and it was probably way back then. And depending on efficiency of the detector, depending on several other factors, these values will be very off. So, yeah, it's really a rough estimate. Yeah. I don't take it too seriously, because, to be honest, I'm so like the dose that I get from working with radioactive stuff is so low that even if I were to make a 2000% error in all of my measurements when it comes to how much radiation I've received, it would still most likely not affect my health at all, because I barely get onto the 100 microsieverts per year. And even if my radiation measurement device is so off when it comes to measuring stuff, wouldn't affect me. Yeah, it's really a lot of variables. It depends on how big you are, like how much mass of you is there to deposit its energy in there, what type of radiation, distance, shielding, clothing, even like the biological factors, like even the hydration level of you. How much water have you drank today? Because most of the energy is deposited in your body, of course, and does radiolysis, splitting water molecules of the 70% water that you have, and then the byproducts of this radiolysis, like the OH radicals that is formed from the radiation hitting the water molecule inside of your body. Most of this stuff, this is the um, stuff that does actually the biological damage, because then you have chemical processes that break down DNA, proteins, and stuff like that. This is where the most of the damage occurs, from indirectly made from radiation. And there are so fucking many variables when it comes to assessing how much radiation damage, biological radiation damage, is produced from a certainly active certain sample of certain nuclides. Yep. Good luck getting an accurate reading. So I don't get this whole fuss about people. Oh no, it's off by 30%. And yeah, I get that, but it's also really complicated calculations. And somewhere you just have to say, okay, this value, take it or leave it. Yeah, really good. Dude, are you working in nuclear chemistry? Because the really stupid thing about being in a nuclear lab and working with radioactive sample, I know I did that, and when it first came to working with really hot samples, like in our neutron source and stuff. Like all of these labs are under negative pressure to prevent any contamination from leaking out. So all of this negative pressure with pre-dried air, you will turn into a raisin after some 5 hours inside of the lab. Dehydrated as fuck, not going to have any water in the lab, of course, no food in labs. And then you're working with radioactive stuff. And after the lab, you feel absolute shit. Dehydrated, dried up like a raisin. And you think, oh man, this was enough radiation for me. I feel so sick. And it's just you being dehydrated and haven't had any food for the last 6 hours in the lab. Most of the time it's that, but when you started to, it's like, shit, I work with the neutron source. Maybe I got a bit too much ready. No, you just dehydrated and didn't have any food for the last 6 hours. But I think that's a feeling most chemists will relate, not only when it comes to radiation, but radiation is really scary sometimes, but also the young students who are just starting out in the first semester, they're coming out back from the lab all dizzy and lightheaded and stuff like that. And I was like, oh, maybe I fucked up and I ingested some cobalt and chloride and something like that. And it's like most of the time you are feeling pretty sick, not from the chemicals, but just because of the lack of water and food and most likely sleep that you had. Do you somehow have a radio code spectrum? Yes! And I will make a video about that. I will probably sell it to Radio Code so they can publish it on their own. But yes, I have a spectrum from it on my phone. Just to clear things up, you can't measure neutrons with a radio code. End of sentence. You can't. What you can measure, what I've measured, are prompt gammas from a neutron capture, but you can't measure neutrons directly with a scintillation counter. That's just not a thing that's possible. Of course, if I'm measuring prompt gammas on my radio code, I was measuring the prompt gammas of the neutron capture of hydrogen and carbon. These prompt gammas that I was measuring can only be created when we have a neutron flux. So there is an indirect proof that I measured something where there was a neutron flux nearby, but I wasn't measuring the neutrons directly. I know Neptunium said that on his video. It was just very unlucky wording, but you can't measure neutrons with a radio code. Yeah, I can make a video about that. Just a general spectrum or like the neutron source spectrum? I would try my best to avoid pulling out the neutron source as best as I can. So I had two peaks, I think 1000 and 2200. It was from the N gamma reaction of hydrogen 1 to hydrogen 2, and from carbon 12 to carbon 13, the second most excited state of the carbon 13 compound nucleus. Because we store our in paraffin, which is basically just carbon and hydrogen. Yeah, I can do that. What's the scariest source in the lab and the safest source? The safest source is our sulfur 35 sodium sulfate solution because you pretty much can't measure anything. Or maybe it's a uranium glass. I mean, we drink out of it all of the time. So, and the scariest source is definitely our neutron source. Yeah. At the moment, it's 65 gigabecquerels of americium mixed with beryllium powder. Yeah. not a great thing to work with. Have you ever treated? Nope, never. I had an MRI scan. That's what they're called. But this doesn't involve any radionuclides. So nope, haven't. Maybe. But I am currently onto trying to make videos about the production of radiopharmaceuticals involving fluorine 18 and maybe something else like technetium 99M. But personally, no. I was injected with gadolinium as a contrast agent when it comes to the MRI scans. Yeah, but it wasn't radioactive. So no, I hadn't. I never had anything radioactive injected into me. Losing my voice here. So, I think that's it for now. Don't know how long this live stream will be online, but might delete this, might not. I don't know. A lot of mistakes, mostly grammar and general speech. Yeah. Hope you liked it. Spread the word. Who is in the chat? I see 11 people watching and 1, 2, 3, 4, 5 people, 6 people typing. 5 are missing. It was really 3 hours, Jesus Christ. And cesium contaminated food and so. I try to limit myself when it comes to videos that only I can make because I have the access to a nuclear lab and all of the other stuff like nuclear watch hands and stuff. Other people can make videos. I will leave that to the other people because I will just do the complicated stuff that actually involves me having a nuclear lab, which is why this partnership between Radiocode and me works so well. And I would try my best to avoid this thing because other people can do this work and they get to sell videos to Radiocode, which is good. And I can do all of the other stuff that they can't. So this is what I did. Yeah. Jay, you just joining? Yeah. We've been here for 3 hours and I just wanted to close it. But if you have a question, since you are constantly commenting stuff and I really love it, feel free to post a question. Auf Wiederhören. The activity tab. Also, I don't think I have used it anywhere, anytime. 12 people. Why are you coming now? I just wanted to end it. Okay. If you have any questions, feel free to write me a DM on Instagram. Simon's Chemiebaukasten. The name is German, but I post all of the English shorts on there. Feel free to ask me anything there. Feel free to ask me on Discord. I'm most of the time active on Instagram, not active on TikTok that much. And yeah, goodbye. It was nice talking to you. I now need something to drink, like a ginger tea, something like that, to restore my voice.